In this video, we want to find limits that are related to physics, and also we want to interpret the results of these limits. In the theory of relativity, the Lorentz contraction formula expresses the length L of an object as the function of its velocity v with respect to the observer, where L0 or L initial is the length of the object at rest, and c in this formula is the speed of light. So when we have an object moving at velocity v, the L0 is the initial length of the object, and the L is the length of the object when the object is moving with velocity v. So as you can see by this formula, the length of the object changes when it has a velocity v. But when the velocity v is a very small number compared to the velocity of or the speed of light, this radical is very close to 1. So the actual length of the object at rest is almost the same as the length of the object when it is moving with velocity v. Now we want to find this limit, which in this limit, as you can see, the velocity of the object is approaching to the speed of light from the left, and we want to see what happens to the length of the object when the speed of the object is close to the speed of light, but of course less than the speed of the light. We want to see what happens to the length of the object. So let's find this limit. We want to find limit of L, which is L0 radical 1 minus v to the 2 over c to the 2 when velocity of the object is approaching to the speed of light from the left. For finding limits, the thing that usually we start with is direct substitution to see if we can find with direct substitution or not. If we plug in c for v, then we have L0 or the length of the object at rest radical 1 minus c2 over c to the 2. C to the 2 over c to the 2 is 1. 1 minus 1 is 0, so the radical is 0. 0 times L0 is 0. So it seems that the length of the object, so this is the length of the object, when the velocity of the object approaches to the speed of light, the length of the object approaches 0. So the length of the object becomes smaller and smaller and smaller, and it approaches to 0 when the speed of the object increases and it gets close to the speed of light. So our interpret is this: when the velocity of the object, when v, velocity of the object, approaches a speed of light, the length of the object approaches 0. Why this limit? The next question that here we have is why the limit is only from the left. One reason that we can give for this question is from mathematics perspective. If you look at this equation, this expression is under square root, and we know that anything that is under square root should be greater than equal 0. If v is greater than c, then this expression under square root, then the radical is undefined. So this means that v, the velocity of the object, cannot approach to the speed of the light from the right side, because then the expression inside the radical would be negative, and because it's negative, the radical is undefined. So this is from mathematics perspective. If v is greater than the speed of light, then the radical is undefined. So for this reason, we have to find the limit only from the left. There is a minus here, attention. But from physics perspective, why the speed of the object approaches the speed of the light from the left? Because in physics we assume that no object can travel with a speed above the light. The speed is always less than the speed of the light for any object, because we consider in physics the speed of the light as infinity, and so no object can reach or passes through the speed of the light. But this is from physics perspective. Here in math we say because the expression would be undefined if the velocity approaches c from the right. Velocity of a falling raindrop at time t is, I have to add v here, is vt or v, where g is acceleration due to gravity in this formula, and v star is the terminal velocity of the raindrop. So we have this formula for velocity of raindrop as a function of time. Vt is v star, which is terminal velocity, so it's a constant, times by 1 minus e to the power of negative g is acceleration due to gravity, t is time, and this v star in the denominator is again terminal velocity. We have this formula, we have this function. We want to find limit of this v, velocity of the raindrop, when t approaches infinity. In physics, never t really approaches infinity. It means that when the time passes enough, for example, after few hours or few minutes, something like that. But here our focus is on the math part of this question. When t approaches infinity, what would be the limit of the velocity of the raindrop? So for finding this limit, we say limit as t approaches infinity of vt. Vt is v star. V star is a constant, times by 1 minus e to the power of negative gt over v star. We want to find this limit. Attention, the variable t is only in the exponent of this exponential function, e to the power of negative gt over v star. When t approaches infinity, what happens in this exponent? What happens to this expression? When t approaches to infinity, negative g is a constant, and as you know, g is 9.8. So we have negative 9.8 times t goes to infinity. So we have a constant, a negative constant, times by infinity. So all of this is negative infinity. This is basically approaching to negative infinity over a constant which is v star. So when t approaches infinity, the exponent of this exponential function, the exponent, this expression, is going toward negative infinity. Now we have to figure out what is the answer of e to a power that power goes to negative infinity. Let me remind you, graph of exponential function e to the x. If you remember graph of e to the x, graph of e to the x is something like this. And as you can see in this graph, when we go far to the right, this graph is going up forever, exponentially. But if we go far to the left, this graph gradually approaches to x-axis. So this means that when x, the exponent, please attention, when the exponent is going toward negative infinity, whatever the exponent is, if it goes to negative infinity, then e to the x is going toward 0 because this graph is gradually moving toward the x-axis. So the distance between the graph and the x-axis gradually becomes smaller and smaller. So e to the x would approach to 0 whenever x approaches to negative infinity. When we go far to the left, the exponential function, when the exponent goes to negative infinity, it approaches to 0. So from my explanation, now we can conclude that because when t approaches infinity, the exponent of the exponential function would approach to negative infinity, the exponential function, the value of the exponential function would approach to 0. So we have this limit equals v star times by 1 minus 0, which would be v star. So at infinity, which means that after enough time, the velocity of the raindrop gradually would approach to v star, which is terminal velocity. And this completely makes sense because it is terminal velocity, which means that finally the velocity would approach to that number.